Richard James will complete these tutorials on simplifying expressions with, of course, the second one, simplifying expressions tutorial 2. Of course, this tutorial is a continuation of the one that we had before, which is, of course, tutorial number 1. It is a continuation of it in more than one ways. Maybe we can take a look at the fact that the last problem that we solved is number 12 there, and now we have 13 here. So we are sure that it is a continuation in that respect. Also, it is a continuation of the same type of problems that we are solving. Therefore, what we have here is somewhat like some of the problems that we have solved on the previous tutorial. And here we are adding fractions and algebraic fractions in particular. We have here add fractions with exclusive denominators. The word exclusive is by no means a mathematical term as it is used right here. It is only a term that is basically a name tag that I use to identify denominators that do not have a common factor. So those denominators that do not have common factors, we call those denominators exclusive. And surely we have a very simple way of adding those fractions that is comprised of 3 phases. The first phase is finding the denominator of the answer, and the denominator is found by multiplying the 2 denominators. Therefore, our new denominator is y multiplied by all of y minus 2. Our first term in the numerator is found by multiplying the numerator of the first by the denominator of the second, like so. And the other term in the numerator is found by multiplying the numerator of the second by the denominator of the first, like that. And there we have in our numerator an algebraic expression. And not only the title of these tutorials are given the name simplify the expressions or simplification of expressions, but in this particular case we also need to simplify that expression. Such a simplification will take into account the simplification of the numerator, and we will simplify the numerator by first expanding the brackets by making use of the distributive law, which states that multiplication is distributive over addition and subtraction. So we will take this 3 and distribute this 3 into the brackets. So 3 times y is equal to 3y. 3 times 2, not quite. Do not forget the sign. 3 times negative 2, and that is equal to negative 6. And what about that one? With nothing to multiply, it will return as it is, without alteration. Lovely. What do we do next? Combine those like terms and do not forget the unique term. So combine those like terms. Those are the like terms, the ones that are in Y, those that are highlighted with those green rectangles. Those are the like terms, and we will combine them. How do we combine like terms? We combine like terms by adding their coefficients. And what are the coefficients? The coefficient here is 3, and the coefficient here is 2. And I will not stop asking my students, what is the coefficient right here? And they will not stop. They will continue to say, it is 2, it is 2, until someone realizes that I am asking so many times to see if there is anyone in the class that will realize that I am making reference to this negative sign that is quite often neglected. So the coefficient here is not 2, but -2. So we will combine those coefficients. 3, -2, 3 minus 2 is 1. Therefore, by combining these two terms, we have 1y. And we know that when we have 1 as a coefficient, we do not need to write it down. We will write down just y. And the unique term will return as it is. And that is also another mistake that students make. When adding algebraic expression, they sometimes neglect, or maybe they do not remember to include that unique term. Or if you have unique terms, we need to include them also. We have a single unique term, and we will include it as it is. Here we have another problem in which we are adding fractions with quote-unquote exclusive denominators. And we will take the same step. The new denominator will be a product of the two denominators. And for the first term in the numerator will be the product of the first numerator and the second denominator, 2a, and the other one will be the product of the first denominator and the second numerator. There we have it. No doubt we will solve by analogy, although the unique term is first on this occasion, and we need also to expand the brackets. What do we say then? The unique term that we have right there is not multiplied by anything at all, so it returns as it is, while the others we will have by expanding those brackets, saying 3 times a is 3a, and also 3 times -3 is equal to -9. What do we do next? The like terms are combined by adding their coefficients, and the unique term is included without alteration. So what about those terms? The like terms, those two are combined by adding their coefficients. No problem with these coefficients. coefficient of 2, coefficient of 3. Add them together, we have 5. So 5a is our answer, and we are finished. No, we are not finished. The unique term will return as it is. Do not forget always to include the unique term. Again, we will solve by analogy. Let's take a look at it. By all means, this one is analogous to this one, and also this one. Take a look at it. Notice where the term in the denominator is the one with more than a single term. We have x plus 1 here, we have y minus 2. So there is a close analogy between this one and this one. The analogy goes a little bit beyond logic, but it also is expanded or extended to physical appearance. So we will go straight ahead and solve by analogy. The product of those two denominators will be the new denominator, and the product of the first numerator and second denominator will be the first term in the new numerator. And then we do this. The product of the second numerator and the first denominator, 4 times x is 4x. We'll go there, and we will do the same thing. Expand the brackets as usual. We are again applying the distributive law that states that multiplication is distributive over addition and subtraction. We will therefore distribute this 3 to each term inside of this bracket by saying 3 times x is 3x, and do not make the same mistake that we generally make by placing 1 here. No, we need to distribute this 3 to the 1 also. 3 times 1 is equal to 3. And what about the unique term? Your favorite just goes right there, unaffected. And what do we do next? We will combine those like terms if we can find them, if they exist. And as it is said, do not forget the unique term. So the like terms are added and the unique term returns as it is. Now we are having somewhat of a nice time, because we do not always want to solve problems that are exactly the same. We want to solve problems that are somewhat different in order that we can demonstrate a little bit of flexibility and adaptability to the problems that we are solving. So here we have one that looks somewhat different, and it's a little bit more than just different. We will add those fractions. As a matter of fact, the sign that we have here is a subtraction sign. Therefore, we will do our subtraction in the same way. What's that same way? The denominator will be the product of those two denominators. And how do we form the numerator? Like that. 2 times all of x plus 1. And what do we say about the sign? Well, when we get there, we will say something about it. 3 times all of x minus 1. And what do we say next? Those two signs. We are saying that the sign that we have here is pertaining to the entire fraction, which is this one. Therefore, when we take the next step, this sign must be pertaining to the entire expression that follows, because the entire expression that follows is as a result of manipulating this second fraction. Therefore, this negative sign that we have right here should precede the rest of the expression. And we are saying the sign is pertaining to the entire fraction and should be the sign of the number that multiplies the brackets right there. What do we do now? Nothing except expanding the two sets of brackets. 2 to be distributed inside, so we have 2 times x, 2x, and do not forget the 2 with the 1 that will give 2. What about this one? The negative 3 with x will give a negative 3x. Do not forget that not only that the 3 is to be distributed inside of this bracket to the negative 1, but the sign also has to be carried. So negative times negative is positive. So we have a positive 3 there. So what do we do next? What do we always do next? Combine like terms. 2x minus 3x, and that is, what about adding numbers that have different signs? Subtract the smaller from the larger, and the answer will take the same sign as the larger. 3 is larger, its sign is negative. Here we have a negative 1x or negative x. Why do we put it here when it is the first one that we arrived at? Because we are sure that the other one will be positive, and mathematicians prefer to put a positive term at the beginning of an expression, especially when it can be done. So we will say 2 plus 3, and that is equal to 5. If you have negative x plus 5, it is not wrong, but it is a little bit more mannerly to put the positive 1 first and the negative after, especially, as I said, if it can be done. But notice what we have done. Negative 1, positive 1. So we have x minus 1, x plus 1. We multiply them here as usual. That's not a problem. All of a sudden, we have x squared minus 1. When we have x plus 1, x minus 1. I am sure that some of the candidates or math campers looking at the algebraic expression that we have right here will have no difficulty seeing how we arrive at x squared minus 1 from right here. But we will take a look at that on the next slide or a subsequent slide. No reinvention of the wheel here. All of the processes that are not discussed in details were explained and over-explained in previous tutorials. So there are quite a few things that we may not have written notes on the screen saying, or we did not go into in any great detail. Surely we have gone through them in previous tutorials, and I am sure that even if you did not view the previous tutorials, then this one should be still clear enough. But it was said in order to remind us that we have previous tutorials in which other principles were discussed in detail, principles that were applied here, and it may do well for some of us if we take a look at the previous tutorials, and maybe a few of us will be just satisfied looking at the one that we have right here, but I'm just making reference to them to indicate that they really exist and they can be found to be useful to some students, candidates, or mathematics campers. On the previous slide, we took this seemingly harsh step of writing x minus 1, x plus 1 as x squared minus 1. And I'm saying that the seemingly harsh step of writing this as this. The fact is that the product is the product of the factors of a difference of two squares. And the product of the factors of a difference of two squares, CXE candidates should be able to identify them. However, we will demonstrate the entire process here. So I'm saying that CXE CSEC students should identify these as the factors of a difference of two squares. A difference of two squares has two factors with terms that are equal, with a single exception, that one of them is accompanied by a negative sign. So we have the same thing here, and we have the same thing here. That's the basic appearance of the factors of a difference of two squares. These two are the same. These two are the same, with the exception of these two signs. So we are very, 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 very competent on expansion. So we go straight ahead. X times x is x squared, and we have, well, what we should have is x times negative 1, which is negative x. Then we have 1 times x, which is x. And then we have 1 multiplied by negative 1, which is negative 1. And we have these two terms that are like terms, and they are the same with the exception of these two signs. They are therefore called additive inverses. So finish up by adding the like terms. They are additive inverses and will eliminate each other. Those two terms are additive inverses and will eliminate each other. The unique terms will return as they are. So those are the unique terms. Therefore, these eliminating each other, x squared minus 1, that's what we have right here. Therefore, if we have this x plus 1 multiplied by all of x minus 1, the result will be x squared minus 1. Therefore, it was not a cheat or a trick that caused us to write x minus 1, x plus 1, the product of those two, by writing that as x squared minus 1. Now we know that x squared minus 1 has two factors, x minus 1 and x plus 1. We have dispelled any reservation about accepting the answer to the problem that we just solved. Because what we should have, adding denominators that do not have a common factor, is that we should multiply the two denominators. But multiplying them result in the difference of two squares. So we just continue writing the difference of two squares as the new denominator. So now that we know that x squared minus 1 has two factors, x minus 1 and x plus 1, we have dispelled any reservation about accepting the answer to the problem that we have just solved. So we have no difficulty with that. But this x squared minus 1 having factors of x minus 1 and x plus 1 has great consequences when we move on to the solution of the other problem. The result is also very useful to the solution of the next problem. So let us take a look at it. The next problem has 4x minus 1, 3x squared minus 1. What do we know? We know that x squared minus 1 has two factors, one of which is x minus 1. So the denominators are x minus 1 and x squared minus 1. We know that the former is a factor of the latter, therefore we do not have exclusive denominators. Therefore, x squared minus 1 is divisible by x minus 1. And we know that any number or expression is divisible by itself. So we know that x squared minus 1, any expression is divisible by itself. X squared minus 1 is divisible by itself. Also, we know that x squared minus 1 has two factors, one of which is x minus 1. So we know for sure that x minus 1 can also go into x squared minus 1. Therefore, the common denominator, which is the LCM of the denominators, is x squared minus 1. This is the LCM. This is the LCM of the denominators because it can go into itself. Anything can go into itself. And we know that x minus 1 is a factor of x squared minus 1, meaning that x minus 1 can divide into x squared minus 1 without leaving a remainder. So this can divide into itself without leaving a remainder, and this can divide into this without leaving a remainder. Therefore, x squared minus 1 is the common denominator. So let us proceed to use common denominator in this particular case. What do we know? We will take a microscopic look at this one, as well as we will do for this one. But let us take a look at the present problem first. What do we say? Well, putting this under the microscope means that each fraction is multiplied by the LCM of the denominators, and the result will be placed in the numerator of the answer. Right. So what do? We take 4 over x minus 1 that we have here, and we multiply that by x squared minus 1 over 1. X minus 1 into x squared minus 1. What will be the result? Well, if we are dividing x minus 1 into x squared minus 1, we may make use of some knowledge that we have already, that x squared minus 1 is the product of x minus 1 and x plus 1. Therefore, when we divide this into x squared minus 1, x minus 1 will cancel x minus 1, and we will have an x plus 1 remaining. Do not forget that this is actually x minus 1 times x plus 1. So x minus 1 will cancel with x minus 1, and x plus 1 will remain. Don't forget that the two factors of x squared minus 1 are x plus 1 and x minus 1. Therefore, if we divide x squared minus 1 by x minus 1, then the answer is x plus 1, because we have, these are the two factors of this. When we say this cancel with this one is left, and we have it right there. And that, of course, we multiply by the 4. Well, this one is a lot easier, because any number divided by itself is equal to 1. So we only have 3 times 1, which is equal to 3. And do not forget this negative sign that we have right here. Nice. Let us finish the solution to the problem on the next slide. There we have it. And we will, of course, simplify this by expanding these. So let us finish by simplifying the numerator of the fraction, and that will be done by what? Multiplying, also multiplying, and then this one will return with nothing to multiply, return as it is. And what do we know? Combine those like terms, and do not forget the unique term. That 4 minus 3 is a positive 1, and the unique term goes back right there as usual. No problem whatsoever. Take a look at the two denominators. They have some close resemblance. Look at this. X minus 3 right here. Well, I'm sure that we are talking about the original statement of the problem. So x minus 3 and 3 minus x. Right. And I pretty much like the appearance of this problem just after maybe this one, because having solved this one, we might not be able, well, we should be able to, but sometimes we get overtaken by the problem that we have solved before, and because of that we are maybe still in the same gear or the same mode of solving a problem like that. So our eyes do not adapt to the reality that we have right there, that these two are very, very much different. We have x minus 1 here, x plus 1. Now we have x minus 3, we have 3 minus x. Maybe some might look at it and say, that's quite similar. Well, maybe in appearance only, but mathematically they are very much different, and the consequences are not really very closely related to each other. But we will take a look at the significance of having denominators written like this. So take a look at the two denominators. They have some close resemblance, but they are not exactly the same. Because they are not the same, most candidates would treat them like typically different denominators when adding fractions. Well, they would eventually arrive at the correct answer, but would be better if they are treated in the way that they should be treated, in a way that indicates that they are very closely related. So take a look at those, and in addition to what I've said before, we'll continue to say, however, the similarities between them is very useful, and if we can make use of it, then our work may be greatly simplified. The similarities that we have between these two may be not what we will expect or would have expected from first glance, but the similarity between them is very useful and may be able to help in simplifying our work. On the next slide, we will demonstrate that x minus 3 is actually equal to the negative of 3 minus x. Therefore, all that we need is a minor adjustment in the signs. So what do we have here? That this is just a negative of this. No doubt then this is the negative of this. Well, if we are thinking like that and we can see that this is the negative of this, all we need to do is put a negative sign for this fraction and change this denominator to exactly look like this one, and that will do it. Let us do as we said, show that x minus 3 is the negative of 3 minus x. It also follows that if the first expression is the negative of the second, then the second is the negative of the first. So we are saying this one is the negative of this, and we will show that. And we are also saying if this one is the negative of this one, then this one is also the negative of that. So let us show that the negative of 3 minus x is equal to x minus 3. So the negative with this 3 will give negative 3. And the negative with the negative x will give a positive x. So negative times negative is positive, and that's all there is to it. So we are sure that the negative of 3 minus x is equal to x minus 3. And as I said before, all we need to do then, if we understand that this is the negative of this, just change the sign to a negative and then change this to x minus 3, and we are done. The converse is also true, that the negative of x minus 3 is equal to 3 minus x. Consider two other properties of numbers. That is what we are about to do. We will not just jump and just do things without considering the underlying mathematical principles that may be involved. So consider two other properties of numbers. Any number multiplied by 1 is equal to itself. Also, we need to consider that negative 1 multiplied by negative 1 is equal to 1. Therefore, if we multiply a number by two occurrences of negative 1, then it is the same as multiplying it by 1, and its value does not change. We also make use of the flexibility of negative 1. That is, multiplying or dividing by negative 1 has the same effect on the value of a number. Multiplying or dividing by a negative 1 has the same effect on a number. Now this one we need to take a second look at. If we multiply a number by 1, the answer is equal to that same number. And that is the reason why we say that 1 is the multiplicative identity. Because if we multiply a number by 1, or expression by 1, the answer will be equal to or identically equal to the number that we multiplied by 1. So let us say that 5 is the multiplicand and 1 is the multiplier. When we multiply by 1, the answer is identically equal to the multiplicand. Therefore, we say that 1 is the multiplicative identity, because if we multiply 1 by another number, or we may say another number by 1, then the answer is exactly or identically equal to the number that we have multiplied by 1. So that is a fact. Also, negative 1 multiplied by negative 1 is equal to 1. Therefore, if we multiply a number by negative 1 and multiply that number by negative 1 again, since negative 1 multiplied by 1 is 1, therefore the result will be that same number. And we will capitalize on that fact as we continue. We are also saying that we will make use of the flexibility of negative 1. That is, multiplying or dividing by negative 1 has the same effect on the value of a number, which is just to change its sign. So if we multiply 5 by negative 1, we will get a negative 5. And if we divide 5 by negative 1, we will get a negative 5. So the result or the effect is the same. Since multiplying or dividing by negative 1 has the same effect on the value of a number, which is just to change its sign, we will take one of the occurrences of negative 1 and multiply the entire fraction, and use the other to multiply the denominator. Let's go. We will take one occurrence of negative 1 right there to multiply the entire fraction, and the other one to multiply the denominator. What are we trying to achieve? We are trying to get the denominators to be the same, because as long as the denominators are the same, all we have to do to add the fraction or subtract is to add or subtract the numerators. Notice that by including negative 1 here and the negative 1 here, overall we have not affected the value of the fraction. But by taking this negative 1 here, it will cause, if we please to write it like that, the sign of the entire fraction to change. And this negative 1 in the denominator will cause the sign of the denominator to change, to the effect that it will be equal to x minus 3. Because we have shown that already on a previous slide, that take negative 1 multiplied by 3 minus x, the result is x minus 3. And this negative 1 here will act to change the sign of the entire fraction. So recall that negative of 3 minus x is x minus 3. So that takes care of the x minus 3. And this negative 1 will take care of the entire fraction. So this negative sign changes this one, negative, and this negative sign changes this one to x minus 3. Now, that seems to be more than enough. And seems also that we might not be able to do that in a few seconds in examination or under examination conditions. Well, it will take some amount of explaining, not necessarily for every student, because I am sure that some of you will see this in less than 5 seconds, but some it will take a little bit longer. Once you have the hang of it, as soon as you see this in an examination or in another, what I would say, forum, you will have no difficulty in making the adjustment in a single second. So if you see A minus B here and B minus A here, what do? You change this one to A minus B and change the sign that you have right there, and you are finished. It is as easy as that. But I cannot just tell you to do that without causing you to be aware of the legitimacy of doing it. And that is why I have gone through these steps to explain. So as I said before, if you had a minus b here and b minus a here, all you do is change this to a minus b and change the sign that you have right there, and that's all there is to it. But I cannot just do it saying that it is correct without demonstrating why it is correct. When adding fractions that have the same denominators, all that we need to do is add the numerators, and the result will go over the common denominator. We have done that myriads of times. So we have the same denominator here, so this will go over the common denominator, and we have 2x minus 6, and that's all there is to it. The result that we have right there represents a greatly simplified version of the original algebraic expression. We are therefore at the stage where candidates may say, "Well done." However, the statement of the problem says simplify. Therefore, if further simplification is possible, then we should follow the instruction, simplify. So let us see if we may simplify any further. As long as it can be simplified, it should be written in a simplified way, or written simpler. There is a common factor of 2 in the numerator. We may therefore take 2 as a common factor. As we can see, 2 can go into 2x, 2 can go into negative 6. Therefore, we have a common factor of 2. So we may take 2 as a common factor. Also, 2x divided by 2 is x, and negative 6 divided by 2 is 3. So we take out the common factor 2 and say what? 2 into 2x, x. 2 into negative 6, negative 3. And there we have 2 times all of x minus 3 over x minus 3. And I am sure that the blind can see that we have factor that is present in the numerator and the denominator. And what do we do if that is the case? If we are simplifying, we may then reduce the fraction by a common factor of x minus 3. And what is left? 2. So the answer for all of this is 2. But sometimes students have a tendency to be a bit absent-minded, especially when we have achieved something that we consider to be great. For example, we are told to simplify this expression, and when we would have gotten here, that would have been a great achievement, and surely a lot simpler than what we had before. But that is not the point. The point is, further simplification is possible. We will therefore simplify a bit further, or we will simplify as much as possible. Here we are now with another of our typical problem. Add fractions with exclusive denominators. The new denominator will be as a result of multiplying or finding the product of the two denominators, and the numerator will be found by first numerator multiplied by second denominator, and then second numerator multiplied by first denominator. And we cannot neglect the sign here, and we are saying it again. The sign is pertaining to the entire fraction and should be the sign of the number that multiplies the brackets. That sign that we have here is pertaining to the entire fraction, and this is pertaining to the entire second fraction. Therefore, we need to include the sign that we have right here also. expand. 3 times 2t, 6t. 3 times 1, no doubt. Then we say what? Negative 2 times 3t, negative 6t. And negative times negative is positive. Lovely. And what do we know? There we have additive inverses. The terms in T are additive inverses and will cancel each other. And no doubt, 3 plus 2 is equal to 5. No problem here. We will continue to add those fractions with exclusive denominators. Common denominator will be the product of those two denominators. And first numerator by second denominator, and second numerator by first denominator. And we will continue. We are taking note on every single occasion. It does not hurt because we are doing tutorials. The sign is pertaining to the entire fraction and should be the sign of a number that multiplies the brackets. And let's go. No problem seeing that that is b squared. B times 3 is 3b. Negative 2b. Do not forget the sign. Negative times negative is positive. No problem. What do we have now? Like terms are combined and unique terms are not to be left out. Notice that we did not say term. We said terms. Unique terms. Right. And those unique terms, we have them right there. Of course, we can have two terms that are unique. Unique means that it is one of a kind. It does not mean that there is only one. It means that it is what? One of a kind. In this expression, we do not have another term like this. And we do not have another term like this. So this one is unique. And this one is unique. And they go in right there. So the answer is b squared plus b plus 10 all over the product of b minus 5 and b plus 3. And no doubt we will continue in the same vein, adding fractions with exclusive denominators in the same way. Those two. What else? Those two. Right there. But let us take a second look at this one, because it might be a little bit simpler than the previous multiplication. No doubt we have the denominator is a product of the two denominators. What do we do next? Like that. See? We are multiplying by 1. Any number multiplied by 1 is equal to itself. 4p plus 3 goes back. No problem. And all that we have here is multiplying by 2. So we may double the other number, but do not forget the negative sign. Negative 2 times p is equal to negative 2p. Do not forget this sign here. But all we are doing is multiply this by 2. 2 times p is 2p. 2 times 2 is 4. But we are maintaining the signs. So this negative 2 times p is negative 2p, and negative 2 times negative 2 is a positive 4. And that's all there is to it. And This is a common mistake that students make when they are adding fractions and sometimes when we are solving a linear equation. We generally take this negative sign and we put it there and then say 2 times p is 2p and 2 times negative 2 is negative 4. But do not forget that this negative sign is pertaining to the entire fraction. So it is negative 2 times negative 2, a positive 4. What do we do next? Combine the like terms. 4p minus 2p. Just subtract one coefficient from the other. 2p is one of those terms in the answer. And 3 plus 4 is equal to 7. And thank him for his grace and favor. A problem that is a bit different from the others, but not unique, because we have solved the problem in these tutorials that are pretty much like this one. So we say what? 4 over x plus 5 over 2x minus x over 2. We will take the common denominator, something that the x can go into, the 2x can go into, and the 2 can go into without leaving a remainder. And we will choose the minimum such term. Therefore, we are sure that if we multiply all of these, x times 2x times 2 will get 4x squared. No doubt, x can go into 4x squared, 2x can go into 4x squared, and 2 can go into 4x squared. But the minimum such expression that the x can go into, the 2 can go into, and the 2x can go into without leaving a remainder, the minimum such expression is 2x. And we normally say what? X into 2x. X cancel x and 4 times 2 is 8. But I'm saying, put that under the microscope. Each fraction is multiplied by the LCM of the denominators and the result will be placed in the numerator of the answer. Or we may say, each fraction is multiplied by the common denominator and the result will be placed in the numerator of the fraction. So we have this 4 over x times 2x. X will cancel x, 4 2's 8. Anything divided by 1, that same thing. We move merrily, 5 over 2x. And what do we say? 5 over 2x. 2x over 1. 2x cancels with 2x and 5 divided by 1 is 5. What about the other one? X over 2. X over 2 times 2x. What will happen? X is cancelled and x times x is x squared. Very nice. So we have the integers are the only like terms and are combined. And the unique term returns as it is. Here we have a problem, of course an applied problem, the same kind of problem that we call worded problem. Let us go ahead and see what the problem is saying in its entirety. In a multiple choice test of 30 items, each candidate is given a bonus mark of 30. A candidate earns 3 marks for each correct answer and loses 1 mark for each incorrect or omitted answer. Assuming that a candidate gets X correct answers, show that the total number of marks received must be divisible by 4. And if you go through Richard James Mathematics Resources, you will see a booklet by the name of steps to success in mathematics. And inside there you will see a problem solving technique known as divide and conquer. And that is the approach that we will take right here. Divide and conquer. So do not imagine that you can just take up the entire paragraph that is written there as a statement of the problem and in one step internalize every single thing and write the answer down in another step. Well, it is not impossible, but it is quite, and I would say very improbable, that students will be able to do that. What do we do? Divide and conquer. And I'm saying, well, one may say that that's horrible or harsh, but I am saying that is the beauty about an applied problem. It contains a lot of details. Sometimes the greatest problem is to decide what bit of detail to include in your solution first. Therefore, the problem that we have right there confronting us immediately is, what will we do first? And we will not do everything at once. We will divide this problem into statements and execute each one step by step by step. And we will see what we have right there. The first bit of detail that we will include: candidate is given a bonus mark of 30. So that is a must. That's an, I would say that is a very good place to begin. Each candidate is given a bonus mark of 30. So there is your answer. No matter what, those 30 bonus marks will be awarded. Therefore, no matter what we will do throughout the entire problem, no matter what all the other problems are statements of the problem or statements within the problem are saying, each candidate will be given at the end, every single candidate will be given 30 marks. Whether you get X right, Y wrong, did not do 5, did not do 20, each candidate will always be given a bonus mark of 30. So you'll take those 30 marks. Then what do we do? A candidate earns 3 marks for each correct answer. Well, we need to know the number of marks that the candidate will get for those correct answers. And we have it right there. Each one, the candidate will get 3 marks for each correct answer. But what is the total number of marks that the candidate will get for correct answer? We need also to know the number of correct answers that the candidate gets. So we know the number of marks for each correct answer, and we know the number of correct answers, because the total number of marks that the candidate will get for those correct answers will be the product of the marks for each one and the total number of correct answers. Now, there are 3 marks awarded for every correct answer. For all correct answers, we need to multiply the number of correct answers, which is X, by the number of marks for each answer, which is 3. So 3x represents the total number of marks for correct answer. We have x correct answers, and each answer is 3 marks. So 3 times x, 3x. That's a bit, but what does it say? In a multiple choice test of how many? 30 items. Loses 1 mark for each incorrect or omitted answer loses 1 mark for each incorrect or omitted answer. Candidate gets X correct answers. But how is this important? We are saying that the candidate gets X correct answer, and we are saying that he loses 1 mark for each incorrect answer. But yet still what we have here is the number of marks for each one. That is correct. But let us see how we put that together in this statement here. It does not matter if the answer is incorrect or omitted. The candidate loses 1 mark. So it does not matter. 1 mark will be lost across the board for everyone that is not answered and for everyone that is answered incorrectly. So it does not matter if the answer is incorrect or omitted, the candidate loses 1 mark. Therefore, for each, there is negative 1 mark. So we have negative 1 mark for each one of those, whether it is omitted or it is incorrect. What about the number of them? How many of them do we have? Because we do not have the number of them, but we need to multiply the number of them by the negative 1 in order to determine how many marks were lost. What about the number of them? The statement of the problem tells us that there are 30 items. That's why this is important. 30 items. And of course, this now is showing to be important to the number of incorrect or omitted, although this is telling us the number of correct. So if X are correct, the remainder is either incorrect or omitted. But it does not matter if it is incorrect or omitted. You will lose the same number of marks. So if X are correct, the remainder is either incorrect or omitted. The statement of the problem tells us that there are 30 items. If X are correct, then the remainder is either incorrect or omitted. Therefore, from those 30, we need to subtract X. Therefore, from those 30, we need to subtract X, resulting in 30 minus X. That is the number of them, 30 minus X. So 30 items in all. X are correct. The remainder will be either incorrect or omitted, which will be represented by 30 minus X. That is the number of them. And for each one, the number of marks is negative 1. So multiplying them together, we get negative 1 times all of 30 minus X. Lovely. What do we do next? We are into the simplification of the expression. So go straight ahead and simplify the expression. Do the multiplication part first, if we please, although we may just write these down, or we may take it for granted that they will go back just the same and then do this part first. Negative 1 multiplied by negative X is a positive X, and we have negative 1 times 30 is negative 30. And what about those two? Those are not being multiplied by anything. They return as they are. Let us combine the like terms. We have additive inverses, and those additive inverses will eliminate each other. Additive inverses, 30 and negative 30. 30 minus 30 is 0. 0 added to anything is that same thing. Therefore, 0 is called what? The additive identity, because when we add 0 to a particular number, the result is that same number. So those will go as 3x plus x. The coefficient of this x is 1. 1 plus 3 is 4, and that's all there is to it. And what do we know? Show that the total number of marks received must be divisible by 4. Well, any number is a product of 4 has to be divisible by 4. All multiples of 4 are divisible by 4. The expression that we have there is unmistakably a multiple of 4. It is therefore divisible by 4 as required in the statement of the problem. This is a multiple of 4 because it is 4 times something. And any number is 4 times something, then that number has to be divisible by 4. Therefore, since we have that number is equal to 4 times something, then that number is divisible by 4. And we were required to show that the total number of marks received must be divisible by 4. And it is. Here we have another problem. As a matter of fact, the entire problem is not written right there. But we are again using the method of divide and conquer. And it is always a very good method to use when we are solving applied problems. A ticket for an adult visiting an exhibition is X cents. There it is, just X. That represents what? The cost of the ticket for the adult is X cents. So there we have the cost of the adult's tickets. A ticket for a child costs 30 cents less. What do we mean by 30 cents less? What do we mean by 30 cents less? Let us say that Jane has 50 cents and Mary has 30 cents less than Jane. How much does Mary have? Well, 30 cents less than 50 cents is equal to 20 cents. How did we arrive at 20 cents? We did that by subtracting 30 cents. We will do the same here. So subtract 30. So if we have somebody having 50 cents and the other one has 30 less, we would subtract 30. So we will do the same there. Not because it is an algebraic expression, then we should treat it differently. Well, we will treat it differently when the circumstance dictates that we do that. But under similar circumstances in mathematics, we do exactly the same thing. Now, what we have there is the cost of a ticket for a child, which is X minus 30. 30 cents less than the adult's ticket. Mr. Smith takes his 3 children to the exhibition. He therefore needs 1 ticket for an adult, and the adult is himself. So he needs 1 ticket for himself because he is taking 3 children. He also needs tickets for his children. Each one costs X minus 30. There are 3 of them. We need to multiply the cost by 3. Which one do we multiply by 3? The cost of those for the children, because we have 3 children. So multiply the cost of those for the children by 3. What happens? In simplifying, X will return as it is and 3 will be used to multiply the contents of the brackets. X goes there. 3 times x is 3x, and 3 times negative 30 is negative 90. And we have been simplifying expressions all day. So combine the like terms and the unique term will return as it is. 4x. That's it. So x plus 3x is 4x, and we subtract 90. Here is another problem. Alice has T tapes and Ben has 10 more tapes than Alice. So Alice has T tapes. No difficulty with that one. What about Ben has 10 more tapes than Alice? What does that mean? What do we mean by 10 more? Let us say that Roy has 4 tapes. Pam has 20 more than Roy. How many tapes does Pam have? Well, 20 more than 40 is equal to 60. And how did we arrive at 60? We did that by adding 20. So Ben has 10 more tapes than Alice. Do the same by adding 10. So 10 more than we add 10. Now what we have there is a number of tapes that Ben has. So we have right there the number of tapes that Ben has. And what do we do with that? We will continue by following the instructions that are given in the statement of the problem. So Alice gives Ben 14 of her tape. What will happen? Alice gives Ben 14 of her tapes. What will happen? Well, the same thing that you imagine will happen. It is not far-fetched. If Alice gives Ben 14 of her tapes, then she will have 14 less tapes than she had before. So if she gives away 14, it follows directly. She will have 14 tapes left. We will therefore take away 14 tapes from the number of tapes that she has. And what will happen to those 14? Those 14 will be given to Ben. So those 14 will also be added to the number that Ben has. So while we subtract 14 from Alice's number, we will add 14 to Ben's number. It is as simple as that. For Ben's number, 10 plus 14 is equal to 24. So T plus 24. Of course, no problem. 10 plus 14 is 24. Ben now has twice as many tapes as Alice. So what do we do? Ben has twice. So because Ben has twice, we will multiply Ben's number by 2. No, we will not do that. Ben has twice as many tapes as Alice. Twice may be taken literally. 2 times. Therefore, we need to multiply by 2. Question is, whose number do we need to multiply by 2? Ben has twice. Therefore, we may be tempted to multiply Ben's amount by 2. However, it is Alice's amount or number of tapes that we need to multiply by 2. There, so we multiply Alice's number by 2. But the statement of the problem may be a little bit misleading. Ben now has twice. Therefore, you are tempted to multiply Ben's number by 2 because it says Ben now has twice. But let's see what the entire statement said. Not just twice, but twice as many tapes as Alice. And we will take a look at that under the microscope. Let us take a quick look at why we multiplied Alice's amount by 2 when we were told that Ben has twice as many as Alice. Let us take a look at why we did that. Let us say that Alice has 30 tapes, as we have right there. If Ben has twice as many, it says Ben has twice. Ben has twice as many. So, if Ben has twice as many tapes as Alice, how many does Ben have? Twice 30 is actually 2 times 30, which is equal to 60. So Ben has twice as many as Alice. Now that we have the values there, which one is multiplied by 2 in order that the two of them may be equal? You multiply Alice's number by 2. And if you take a look at it in another way, we may also take a look at it from the other direction. Ben has 80 tapes, and that represents twice as many as Alice. So that is twice the number that Alice has. So 80 is twice which number? 40. So Alice will have 40. So that being the case, how many tapes does Alice have? 80 is twice which number? 80 is twice what? 80 is twice 40. Therefore, Alice has 40 tapes. Because Ben has twice. The number that Ben has is twice the number that Alice has. In this case also, whose number do we multiply by 2 in order that the two values may be equal? For equality, we will multiply Alice's number. Right, so Ben has twice the number that Alice has. So Ben has 80, twice the number that Alice has. So Alice will have 40. Alice has 30 and Ben has twice this number, twice the number that Alice has. So Ben will have 60. There is no doubt that by the way that the problem is worded, we might be tempted to multiply Ben's number by 2. Sometimes when we are solving applied problems, we need to place our answer under scrutiny in order to verify that we have done the correct thing. Maybe we would want to throw in a few values to ensure that our answer is not in defiance of simple logic and common sense. So when we have a problem, a worded problem, sometimes we may be tempted to just do things off the top of our heads. But if we take a second look at what we have right there, we might realize that after submitting our most glorious solution, that we would have misinterpreted maybe just a single word placed at a strategic point, and then that would have thrown off our entire answer. What is good is our ability to check again our answer to see if it is correct, because it makes perfect sense. If Ben has twice as many as Alice, well, it might not appear to be so immediately, but when you put some numbers down and say which one is twice which one, then we find that it is not difficult to come to the conclusion that we need to come to. And sometimes we need to ask ourselves questions when we are solving applied problems and also other problems. Finally, Adam scored X points. Imran scored 3 points fewer than Adam. Shakil scored twice as many points as Imran. Together they scored 39 points. Read that again. Adam scored X points. Imran scored 3 points fewer than Adam. Shakil scored twice as many points as Imran. Together, they scored 39 points. And those who are especially familiar with sports, Adam scoring points would tell me that Adam is playing cricket. Adam Gilchrist, that plays cricket for Australia. Wicketkeeper batsman, maybe the greatest of all time. Shaquille O'Neal is playing basketball. And we have, as we said, Adam Gilchrist. But the greatest of them all is Imran Khan, the all-rounder who was also captain of Pakistan. So there we have, if we can identify the names and associate them with sports, Adam Gilchrist, Imran Khan, and Shaquille O'Neal. Let's go. So Adam scored X points. That's not difficult. What about Imran, who scored 3 points fewer? What does 3 fewer mean? 3 points fewer is the same as 3 points less. We therefore reduce Adam's score by 3 by subtracting 3. Well, I imagine that the examiners did not intend us to associate these individuals with different sports. Maybe it does not matter, because it's just a mathematical problem that is stated in that way. But I would imagine that all 3 of them would be playing the same sport, and maybe that's basketball, because the numbers in cricket are not called points, but they are called runs. So 3 points fewer is the same as 3 points less. We therefore reduce Adam's score by 3 by subtracting 3. Shakil scored twice as many points as Imran. Twice as many. Twice is the same as 2 times, both in mathematics and English. Multiply Imran's score by 2 and give that to Shakil. So Shakil scored twice, 2 times as many points as Imran. Take Imran's points, multiply that by 2, and hand them to Shakil, and that is what we get. Together they scored 39 points. The word together is one of the greatest indicators of sum in a problem. Put them together, find the sum. Also, the total is equal to 39. Therefore, the sum is equal to 39. So we add them, and the result is 39. So Adam is X points. Imran, 3 fewer, minus 3. Shakil, twice, so 2 times. And then together they score 39. Add to get together, they score 39. So the word together is one of the greatest indicators of sum. Also, the total is 39. Therefore, the sum is equal to 39, as we have indicated right there. The statement of the problem also required that we write down an expression for Shakil's score. So the expression for Shakil's score was a requirement of the problem. So we are highlighting it there. So the statement of the problem also required that we write down an expression for Shakil's score, in addition to the equation that may be solved in order to arrive at the value for x. We also need to take note that the statement did not require that we solve the problem, just that we should write the equation that may be solved to give a value for x. It did not require that we find the value or a value for x.